my thought before I hand off to my teammate Stan. Key takeaways that we are just going mainstream. There's no doubt about it in our minds. There were some hiccups, but I think we are seeing that there are some telltale signs that this is going to pick up lots of steam. There are challenges, by the way. It's still not completely there as yet. I talked about quality, performance, freedom from bias, and of course affordability. And then what are we doing? What is Intel's role to get us to mainstream? So that concludes my talk, and again, thank you for your time this morning, and I'm really excited and honored to be here. My next speaker here, the colleague, is Stan Barron. We'll talk about 18360 VR manipulation.
So thank you, Nilesh. I'm Stan Barron. So Nilesh talked about bringing VR to the mainstream and how that's happening in the industry. One area where I think we'll hit first is video, VR video. So I think this is going to be one of those key mainstream uses. So the agenda for this part of the talk will be about the ecosystem for video, the Intel platform and how it accelerates and enhances the VR video experience. And I'll show you a look at a content creation pipeline in some areas where you can innovate and improve on this usage. And then I'll show an example pipeline and some of the challenges in that pipeline. So here's a look at some of the devices out there for capturing 360 video. This is just a snapshot. There's actually more than these. Not all these are products. Some are products. On the left, you have some of the simpler devices that are more cost effective. They range from a couple $100 all the way to the right, where you can get in the tens of thousands of dollars for these devices. And you can see there's a few different types here. One is using sort of fisheye lenses to capture a bigger picture of the world with a single lens. And others are using multiple lenses and sensors to get little pieces of the world and stitching it all together. So the VR ecosystem. Here at the beginning you have the capture. So there's a couple different types of devices here, like I talked about a little already. At the bottom you have these PC-dependent devices. And what I mean by that is like a GoPro device where you capture the content and then you transfer it over to your computer to do video editing or production of the system. And this rig here is an example of a bunch of GoPro cameras put together in a cylinder so that you can capture a 360 view of the world. Up above there is a fully autonomous system that does everything in one device. And from here, you can send your streams to the cloud or transfer to a PC, like in the case of the GoPro system. And here's where you're doing all your stitching, your editing, and getting your content ready for consumption. From there, you either generate a file with this content or you stream over a network to an end device where you're going to play that back. So this could be played back on a two-dimensional monitor like we have in our laptops and desktops, or to an HMD. Now, these HMDs or head-mounted displays come in a few flavors too. There's a fully autonomous kind, which is an all-in-one device where all the compute is on the HMD. Or you may use your phone inside of a kind of a phone add-on, like the Gear VR, and that's an all-in-one device doing display. Or you can have a PC-dependent. This is like the Oculus Rift or the HTC Vive, where you're using the compute of the platform to do all the rendering, much like you saw in Nilesh's part, where all the processing on the CPU and GPU is going on a PC device. And that's more of a display that's a simpler display in some ways, where it just has the sensors and all the compute is left to your PC platform. Okay, so here's a look at some of the consumption devices. And one of the reasons we believe this is real is because so many people are building these devices, right? So again, you have a bunch of these different products. In the top right there, you have an Intel announced product or concept called Alloy. Also, so a lot of this content can be seen on, from phone, tablet, and PC. Okay, so onto the architecture here. So again, on the left, we have the device doing capturing. A lot of the content can come over encoded because you're limited by your bandwidth coming to the platform. So there's a decode that happens. There can be some pre-processing that's cleaning up the video, making improvements to the video. And then in the case of multiple sensors, you need to bring the different camera views together into one continuous view of the world. And that's where the stitching comes in. And then this is often mapped into a format, such as a cube map or a sphere map of the world. And that's how your content is stored, actually, as it's transmitted through the system or onto your hard drive. Sometimes this is then encoded, like if you're going to ship this off across the network, you then have to encode it to make sure you lower the bit rate to transmit bit rate levels. And then you put in a file format, say MP4 or something like that. You might wrap it in that so that it has a standard way for somebody to play it back. So the Intel platform here in the middle is involved in all of these steps. It's doing processing for all of these here. In one place, these blocks in the dotted lines, these are areas where people are innovating and doing, adding their algorithms to the process. And a lot of them are doing it on OpenCL. That's one way that you can take advantage of the graphics portion of the Intel platform, as well as other graphics devices out there. So this platform could be a PC in the case of the demo we have out there. It's a small nook doing all of its devices, so it's a little box doing it. Or it could be a server on the cloud, and Intel has platforms for both parts. The cloud gives you the more compute, but you're going to have some latency going back and forth to the cloud. So if you need some sort of real-time preview, you want to see what you're doing right now, that's where the laptop or some sort of system like that would make sense. Okay, and then on the right is the render side of it, and Nilesh went over that quite a bit on how the render happens on the platform. So the Intel platform, it provides the hardware that accelerates and enhances this experience. We support most of the industry codecs. This is like H.264, H.265. These are encoding standards. And then there's a mechanism to provide your innovations, to provide additional IP or intellectual property to enhance the system. And you can do that just in like OpenCL or other industry APIs, such as DirectX or OpenGL shaders. VR, we're seeing it doesn't behave exactly like other media content out there. So there are standards-wise trying to come up with what's a better way to encode 360 content versus your rectangular content you're getting now through Netflix or through your TV, right? That's got a certain type of content to it. It might be 1080p or moving to 4K, but it's still a rectangle. So is there a better way to encode this full 360? And then if you're going to have a head-mounted display, you might want a stereo look so you see depth. So is there a better way to encode stereo content? And then also file containers for this. If you want to know the shape of where your cameras are relative to each other, you might want that metadata to do something else. You might want other information, such as video analytics in the system. And so we need to invent other file formats and containers for passing around this kind of content. So here I'll take a little look at a VR creation pipeline. So this is an example of, from beginning to end, what you would do to create VR video content. So in the beginning you have your cameras. Your camera rig, from the images I showed before, you have to know how those cameras are placed relative to each other, their relation to each other, sometimes called camera extrinsics. And some things you can do in here are rotations and translations to line them up so they're seeing the world lined up in a similar view. So you have maybe this table here is being looked at by two cameras. It should line up and look like a straight line table and not have come in at a bend or an angle, right? So per camera you have to align them in this hardware to make sure they're all sort of synchronized in one view of the world. And then you have to do per camera your compensation. This happens in every camera now, making sure you're not having a really dark or really light image, right? Now the challenge is that happens on any camera. Now, when you have multiple cameras, you have to put global adjustments to this. So one thing is, if the shape of your capture device is a sphere, these all have to be projected on a sphere so that they are capturing a sphere, not little rectangles of the world. Or a cylinder, in the case of the demo out there, they're just capturing a cylinder. And then the alignment happens between them. So one way you automatically align it is by doing feature matching. So there's different ways to extract features from the video content, and then you want to match them up so that you find exactly where these two cameras align. This can be done in hardware, but hardware is never perfect. If a camera moves a little bit, you want to be able to realign it with an algorithmic method. And that's one way to do that is feature matching and between the two cameras. Another part here is to do global compensation. So each camera is independently compensated for, say, exposure, but they've done it independently of each other. So one scene may still be a little darker than the other, so you have a global exposure compensation. And in the demo outside, I can show you that. There's a key, turn that on and off, where you can see if you're compensating globally or not for exposures, what it'll look like. And it's to avoid dark regions in the end content. Okay, then the next part is stitching. So whenever you have more than one camera and you want to combine the views, what you do there we call stitching. The first step in stitching is to find some sort of seam or where the two overlap. So one thing is you can just pick the midpoint, or you can do some sort of graph theory approach, which is minimizing the energy through the system. So a low energy portion of the system might be like a flat wall that doesn't have a lot of details. That's better to cut the seam through that than a high energy system, which might be a person. Right? We have a lot of features, a lot of details. If you put the seam directly through a person, you're going to see an artifact there. So you'd rather put the seam in a low energy section. Another important part is what's called parallax removal. So in this system of VR, there's good parallax and bad parallax. Good parallax is where you have stereo cameras and you're getting stereo vision that gives you a sense of depth. And bad parallax in this case is when you have the two cameras that have a different view of the world, but you want to make it a seamless view. You're trying to see one view of the world, but these cameras have a parallax between them. So this parallax removal is the idea of bringing them together to the same view of the world. So an example, in between two cameras you get this disparity at different distances. This is what gives us our depth perception. When you don't want that depth perception, so it's just one of your eyes that you're stitching together and not the other eye, you may take these different disparities and kind of work them together so that you have no disparity, and then that would remove this sort of parallax effect. And there's different algorithms for this. This is one area for innovation in this space. Dense stereo, multi-plane perspective sweeps, belief propagation, optical flow. These are all pretty well-researched areas of getting rid of that effect along the seam, which I can show you in the demo. But there are going to be other algorithms developed. That's something that you could do. I think machine learning might be an approach that would have a breakthrough in this area too. And then the last step is blending. So you create the seam and you try and remove parallax, but it's still not perfect. You sort of blend away things. That's another step in the process that's pretty compute intensive. Okay, so then after that you package it, and I won't talk too much about this, but there's different formats out there for how you package this content, and so it can play back on any VR device. So areas for innovation, I think I talked a little bit about this. One's making it visually seamless. You don't want to see the seams between the camera views. Another area is once you have this 360 view of the world, what are you going to do with it? Right? One thing is to look at computer vision and other analytics. And another thing is when you have this 360 content and you're playing it back, how do you direct the end user to what's interesting in the video? Say you're producing a movie and you want to direct their attention to a particular part of the movie, but they're not looking there. So how do you get their attention back there? Right? Maybe you have a noise, a loud sound to get the user to turn around. Or maybe there's an arrow saying, go look that way. Right? So how do you get a user to interact in this 360 world where you don't know where they're looking? Okay. And then I said earlier the 360 aware formats and coding schemes, etc. And then one of the reasons why we have this 360 view of the world, well, you can have a video playback content, like someone made a movie, or this camera rig is in a sporting event or at a concert, and you get to have the best seat in the house. So in the front row of a basketball game, you put the camera, and now you get to have virtual front row tickets to the basketball game and experience it as if you were in a front row seat. The other thing is when you're doing something like AR or mixed reality, you want a vision of the entire world. Maybe you're doing a 3D reconstruction of the world on the fly. Well, if you just have your cameras in the front, you can do the 3D reconstruction only where you're looking. But if you have a 360 camera rig, you can do reconstruction or other things even where you're not looking in preparation for when you turn to look or go there. So it gives you a way to look at your environment more holistically instead of at just a viewpoint. So I think it's a key to doing just pure video for VR, but also for augmented reality and mixed reality. So here's an example of the stitching pipeline, where input images are coming in and they're doing those things that I talked about before, right? You're finding features, matching them together to line the cameras. Then you're warping the images into a cylindrical or sphere. You're finding the seams. You're doing exposure compensation. You're blending them together. So I talked a little bit about parallax. Here's an example of it. In the top right, here's an image of two eyes, viewpoint A, viewpoint B, looking at an object, right? And down below, you can see what each sees. So viewpoint A sees the star, but it sees it with a blue background, because that's how it looks at from an angle. Viewpoint B sees the star, but with a red background. Now, how do you combine two views where, yeah, you might get the star right, but are you going to have a blue background or a red-black background when you combine them? So this is the issue with parallax effect. So another example is this image at the bottom, where the cameras are slightly rotated. So they're seeing this person, but they're seeing a slightly rotated angle of them. Now when you go to combine them, one face is looking in this way, the other part of this face is looking in that way, and you combine them together, it doesn't look right. So that's the parallax challenge I was talking about, and that's where the innovation needs to be, to remove that parallax and make it seamless if you're going to use multiple cameras for capturing the world. So that was a look at one of the mainstream usages that will be first to VR. And Dr. Sudhir will talk about some of the future usages and where we see this moving. And